Which of the following can be classified as a reduction and oxidation reaction? This one can be tricky, and it's extra irritating that it split the page like that or split the line like that. So how can we go through and do this? So first and foremost, one of the things to watch out for is it's not asking what species was oxidized. It's not asking what species was reduced. We don't care. Okay? All we care about is, does the oxidation state change? Okay? Was something reduced? Was something oxidized? So you could go through and determine the oxidation state for every single atom on both the reactant and product side, and that's perfectly legitimate and is a valid approach to this. Right? If we were looking for a more involved kind of answer, how many electrons were not this class? What was oxidized or what was reduced? Okay? You're looking more at the amounts of electrons and where and what was gained, lost, and all of that. We don't need that. All we need to find is, did it change? Okay? So what we want to do is shortcut that process as much as possible. Okay, so where I'm going to shortcut it for the moment is we're just going to look at answer choice B. And in particular, I'm going to look at that oxygen. What is special about that oxygen? It is diatomic. Keep going. Its oxidation state doesn't change. All I'm looking at is a single oxygen, so its oxidation state changing is challenging because all I'm asking you to look at is to get just that. What is special about that? What? There's only a single element, yeah. What does that mean? Particularly as it pertains to reduction and oxidation. Whether it can or cannot be reduced is beside the point. The point here is just looking at that oxygen. What would I have to figure out? If I was going to determine anything about oxidation state, what do I have to do? What's its charge? Okay, so this is where we get -2. No, it's not -2. Its charge is 0. Upper right-hand corner, it's 0. Okay, how many oxygens are there? 2 times its oxidation state. What must the oxidation state be? 0. Okay, one of the quote-unquote rules that is typically kind of spot out about reduction and oxidation is that you should memorize anything in its elemental state is a 0 oxidation state. Yeah, you can do that, or if you just follow the rules that you're told to follow, it's trivial. The oxidation state for that oxygen is 0. Okay? People were asking about, well, how is it changing? All I'm looking at is that one thing. Now we can cross the bridge of what happens to it. And the what happens to it means I have to go through and I have to look at everything else that was present. Okay, so I'm going to look to the product side of that equation. And I see oxygen show up in a couple different places. What is the oxidation state in those other places? Okay, so we're hearing a lot of zeros. How would we determine oxidation state? Let's take a look at the oxidation state within water. There's 2 hydrogens times an unknown oxidation state plus 1 oxygen times its unknown oxidation state, and this equals an overall charge of 0. One equation with 2 unknowns. How do we solve? What's that? System of equations requires a second equation, which technically we have. What's the oxidation state for oxygen? Don't look at that. It's -2. When does oxygen have a -2 oxidation state? When it was by itself, did it have a -2 oxidation state? No, so it does not have a -2 when it's by itself. when it's combined with something else. Why? What is special about oxygen? It's electronegative, which means when we bind oxygen to anything, what's it going to do? Take all the electrons, which is why it carries the -2. Okay, it's not always that, and we'll come back to that in a second, but that means when I see oxygen in the product, what is that Y? It's -2. Do I care what the hydrogen is? No, 100% irrelevant for this question. The question asks, did we do a reduction or oxidation? Did oxygen change its oxidation state? Yes, which means we did redox. I don't care what happened to the oxygen. Okay? I don't even necessarily care what its oxidation state was in any individual case. I just need to know that it changed. As long as it is changed, I had to have transferred electrons, which means I had to have done a reduction or an oxidation reaction. Okay? This is challenging because you're dealing with oxidation states, and oxidation states are hard to work with. They're very easily confused, and there's a bunch of different things that kind of stack into it depending on how you want to go through and interpret it. Is oxygen always a -2? Clearly not, because we started with oxygen at the beginning where it wasn't a -2. Why was oxygen a -2?
Connected bond to something.
No, not connected to bond to something else necessarily. Nope. Why was oxygen a -2? No. It's bonded to something in O2 too. You provided the answer for why it was a -2 earlier. It's electronegative. Oxygen is the second most electronegative element on the periodic table, which means what's it going to do whenever you put it into a bond? Steal the electrons. That's what it does. It's going to take the electrons away from whatever it's bonded to. Okay, are there exceptions? What happens when you bond oxygen to oxygen? Which oxygen has a larger electronegativity? They don't. Which means they don't get to steal electrons from the other one. They have to share equally. And if they share equally, cancels out and you get a zero oxidation state. There's one exception beyond that. When I bond oxygen to fluorine, fluorine takes the electrons away from the oxygen, which is why the oxygen won't be a -2 then either. Okay, so it's coming down to oxygen's ability to take electrons from another atom. Okay, that's a real nuanced or kind of complicated thing to deal with. Here, we don't care, we just cared that it changed. And we picked oxygen, hopefully because we knew oxygen, its oxidation state would always be a -2, like that's the big one, okay, except when bonded to oxygen. So what does that mean? What's our answer? B. Unless, of course, there's another answer choice that includes B. Is there another answer choice that includes B?
D.
Dang, all of the above. Which means what do we have to do? We need to go through and check the other ones. Okay? But we picked B as our starting point because B was supposed to be our easier one. When we had the element all by itself, what was its oxidation state? 0. When we bond it to something else, what happens to its oxidation state? It's going to change. So let's take a look at answer choice A, which I know the A has disappeared. Okay, I'm going to look here, right at that one. Why? It's carbon all by itself. When I look to the product, it's not by itself, which means it's changed. And if its oxidation state is changed, that's redox. How did it change? I don't know. Don't care. All I'm trying to do is get through what the question is asked. Did it transfer electrons? It had to have. Okay, look at answer choice C. I see gold all by itself, which means its oxidation state is 0. Go over here. It's with something else. It had to have changed. And if it's changed, that's reduction or oxidation. Which then means the answer is all of the above. Yes, sir.
Is it safe to say that all single replacement reactions are redox reactions?
All single replacement reactions are redox reactions, yes.
So I can
That-
look at that, and if I know that they're single replacement, I just figure it out like that.
Which one of those equations is single replacement? But the carbon isn't swapping in for the lithium. Yeah, I don't know that I would say any of those fit the pattern of a single replacement reaction. Okay, but you're right. It's true. It's just none of those really fit that pattern. Okay, and I think A has further issues. There's something about balancing, maybe. Maybe that got fixed. No, it's not balanced. Like, there's all sorts of weird things going on within A. That's because the chemistry happening in A is crazy. But again, we don't care. We don't care what the chemistry is. We're just caring that it was a reduction in oxidation.
So there was no like isolated ones that are by themselves. Would it just be like carbon dioxide, for example, the oxygen has like a -2 in that. So like if it changes in the right side in another compound, would that just be redox as well? So right now we're just doing one of those like isolated neutral elements. Just like in a compound, like if there wasn't any neutral ones, like would it be any different or just?
I don't understand your question at all. I'm not even sure I heard a question.
Well, all the ones we did, they have an AU solid, like they're single elements, so they're neutral. I mean, they're easier ones to do. Like if it was just compounds, like would it just be?
So I think I'm picking it up now. So if we look through at these examples, what we'll notice is that every single one of these had an element by itself. Okay? Does that mean every element by itself is going to have a zero oxidation state? No, why not? Okay, it could very well be an ion. Okay? So in all of these cases, you were given elements by themselves, yes, okay, that changed into a new compound. Yes. Okay? Why were those selected? Because the other option is we don't give you an element by itself. And if we don't give you an element by itself, what must you do? You got to determine the oxidation state for every single atom all the way through, because there's no shortcut that allows you to navigate it. Does that make sense?
So you have to do it for every single one, and you can't just isolate a single one?
You can't just isolate a single one. You would have to do it for every single one. If you got lucky and the one you picked changed, you're done. But if you got unlucky and picked one that didn't change, you could be saying no when it actually was. Kind of makes sense? I wonder if it was just random chance that all three of these had equations that were involved a single element by itself. Random chance or design? Next question. Or are we sufficiently done with that question? You happy, Brock?
Yes, thank you.
31, we've got this big long equation here. Relevant for everybody because what we're looking at is a combustion of glucose into carbon dioxide and water, also known as respiration, or parts of our respiration. Okay, so we want to know what is the limiting reagent if 2 moles of sugar and 8 moles of oxygen are reacted in the muscles. Okay, this question is effectively a limiting reagent calculation. It is, it actually says it. Okay, but when we talk about limiting reagents, typically when we think about them as theoretical yields, percent yield calculations. And to go through and do those, how many equation solves do you need to go through and solve this? 2. You need 2. Okay? So we could go through and brute force 2 equations all the way through this. Okay? But ultimately, the only thing that we're trying to do, even when we did 2 equations, and everybody loves the cheese sandwich, so let's deal with that. Our 2 slices of bread plus our 1 slice of cheese, right? Sets us up with our one sandwich. We went through and we converted the bread into sandwiches. And then we also go through and we convert our cheese into sandwiches. That was our calculation. And whichever one produced the smaller number of sandwiches, that was our answer, right? Vaguely ring a bell? Right. The whole point of going through that process was kind of twofold. One, we wanted to figure out how many sandwiches we could make. So that was part of my answer. Right? The other part of it is I had to know which one was the limiting reagent, which one limited the output. Okay, so there's technically two pieces of information we're solving in that approach, which is why we had to do the calculation twice. Do I need to know how much product is produced? This question doesn't ask for that. So I don't actually have to take it all the way to sandwiches. All I have to do is get the units into a system that allows me to compare. And when we do the two equation solve, all we're ultimately doing is getting the units into a singular unit system. I can't compare bread to cheese, but I can compare sandwiches to sandwiches. All right? So I can set this equation up as the two solve, and I'll go through and do this real quickly. What product do I want to solve for? CO2, good answer. Okay. Mostly a good answer, and typically we're solving for grams. Don't correct me if I'm wrong, because I'm probably wrong. 44 grams of CO2 is 1 mole of CO2. Moles of CO2, I want to convert into moles of, what do we got? Sugar. Just call that shug, why not? And then moles of shug. Do I know how many moles of shug I had? Yeah, 2. Do I know the mole ratio? 1 mole of sugar was 6 moles of CO2. And I could go through and I could do my math. It's not 12, it's going to be 12 times 44. Finishing out the calculation, which would be our grams of CO2. Okay, that was effectively my bread. We could go through and run our cheese. And this time you'll note that I'm actually writing it differently. Okay, why am I going through and writing it slightly differently this time? Whoops. I need to pay attention to my numbers though. Why can I write it differently this time? What do you notice? How different are those calculations? They're not different. Once I've established what the process is for one, I just repeat the process with a new unit system, and I just now swap in that new unit wherever it needs to go. So if I've used my brain once, I now just have to copy my brain for the second time. I can now punch it in the calculator and I get whatever answer it is. So we're going to get 8 times 44 for the blue. Okay, 4 grams of CO2, and for the black, what do we say, 12 times 44? Okay. We got to ensure our mole ratio was correct. We had 6 moles of CO2 was 1 mole of sugar. 6 moles CO2 was 6 moles of oxygen. We got our 8 moles. It looks like everything's aligned correctly. So 12 times 44 is a significantly larger number than 8 times 44, which means what's my limiting reagent? The bottom one is the limiting reagent. What was the reagent in the bottom one? The moles of oxygen. Okay, so we go, oh, that's my limiting reagent.
Do we have to solve it in grams like that to find the limiting reagent?
Okay, so what we went through and did with this particular example, and I did it fast. You notice in typical cases we talk through things, right? And I didn't talk through any of it. I just said, this is what we do. Okay, do you need to solve it to grams? No. What do you need to solve it to? The same units, period. What units do you want to solve to? Okay, moles is only half the answer. So let's delete all that. That was all that work. And I'm going to switch this up a little bit differently. I'm going to say I want to know how many moles of oxygen are necessary to react with 2 moles of sugar. The moles of sugar needs to go in the denominator, so that unit cancels, right? What unit do I want to appear in the numerator? Moles of oxygen, right? Okay. Where do I find the conversion factor for that? It's the coefficient for my balanced chemical equation. 6 moles of oxygen is 1 mole of sugar. So to react 2 moles of sugar, I need 12 moles of oxygen. How many moles of oxygen do I have? I have 8 moles of oxygen, which means oxygen is my limiting reagent. Done. I get to the exact same answer, but I'm doing far less calculations. Why can I do that? That's what the question is asking. And it's going to come to your comfort level with how you interpret what the question is asking versus how you go through and solve. If you're not comfortable with that interpretation, what do? Bulk calculate the crap out of everything and hope for the best. Okay, it will take more time. Okay, because it's taking more time, that potentially detracts from your ability to answer other questions. Should it? Yeah, because you don't know the content quite as well. That's why you get less time. Somebody who knows the content better and recognizes the patterns behind these calculations, because they've run a ton of calculations, can now short-circuit it and now has more time to spend in harder questions. Absolutely makes perfect logistical sense. And it's just going to come down to where your focal point is and how you answer those questions. Okay? Limiting reagent calculations only come down to getting into the same units. Okay? Right out of the gate, I have 2 moles of sugar and 8 moles of oxygen. Oh, 2 moles of sugar is less than 8, so sugar must be the limiting reagent. Was it? Oh, no, it wasn't. You mean we actually had to run calculations so that we can get the numbers into a unit system that allows us to compare? Yes, that's the whole point. So you have to decide which track you want to navigate. Do you want to track and just say, well, all I'm being asked for is what the limiting reagent is? Zero straight to getting the units into a system that allows you to make that comparison. Got it? Done. Or you go through longhand and you say how much product would be produced. Both are going to get you to the same conclusion with varying amounts of work. Okay? I would argue this approach that we just went through and did involves a little bit more brain power to recognize what's happening within it. During an exam, you're probably brain stressed, so it probably makes sense to lean on the things you already know and brute force calculate. Brute force doesn't require as much brain power, so you can conserve that brain power for later. Does that answer your question? Okay. Did I have to convert the 2 moles of sugar into oxygen? What if I converted the oxygen into sugar? Would that work? Yeah, it should. You do it. And see if we get to the same conclusion. Again, what am I asking for? I want to know how many moles of sugar I need if I react 8 moles of oxygen. Set up your calculation, work through it. Is moles of oxygen the same thing as moles of sugar? Nope. So what has to happen? I need a conversion, and I want my moles of oxygen to cancel, so I'll place it in the denominator. What do I want to appear? Moles of sugar. Does that conversion factor exist? That comes from my balanced chemical equation. The number in front of my sugar is 1. The number in front of my oxygen is 6. 8 divided by 6 is, thank you, 1.33. So to react all 8 moles of oxygen, I need 1.33 moles of sugar. How many moles of sugar do I have? I have 2 moles of sugar. What does that mean? There's an excess of sugar, right? I have 2 and I only need 1.33. And if there's an excess of sugar, what does that make it? The reagent in excess. The question asks for the limiting reagent, which means it's not sugar, it must be oxygen. And I get to the exact same conclusion. All you're trying to do is get the units into a system that allows you to compare. That's it. And depending on the question asked, you don't have to do as much work. You just have to pay attention to what the question is actually asking. Make sense? General rule of thumb. The multiple choice don't ask you to show work, right? Which means how many calculations do you think you should be running in a show your work question? A whole lot or very little? Very little. Because if it was a whole lot of calculations, what do I, as the instructor, probably want to see? What calculations are you running? Why? 2 reasons. 1, to prove that you know what you're doing, and 2, so I can give you partial credit. Because a multiple choice, you could get this wrong if you ran half an hour of calculations and getting it wrong at the end. All wrong is a bit obnoxious. Right? So if you're looking at a multiple choice and it's taking you a long time to set up, you're probably looking at it wrong. And you should pause and move on, first and foremost, because you're already brain dead from all the work that you've done. Move on, come back to it later. Don't look at your work and see if something has jogged loose, how to go through and approach that question with less calculations. Okay? But the show your work the multiple choice will still ask for calculations. They should just be relatively minimal. 1, maybe 2 calculations. Hopefully. Make sense? Okay. All right. We should be following this. It's a conversion process. All conversions, we run the exact same thing. Okay, we want to identify what do we want. We want liters. We want liters of a solution. Okay, what are we given? 0.4505 moles of sodium iodide. And we're given 0.724 capital M. What should we do as soon as we see capital M? Moles of sodium iodide per 1 liter of solution. Same approach as always. I want liters of solution. I go back to my given information. Does my given information give me anything about liters of solution? Yeah, it does. That red one gives me something about it. Okay, but it's placed it in the denominator. Where do I want liters of solution? In the numerator, so I can flip it. 1 liter of solution, moles of our sodium iodide, 0.724. All right, cool, that gets me liters of solution, but it brings in moles of sodium iodide. Do I want moles of sodium iodide? Nope, so what do I got to do? Cancel it out. So I could write moles of sodium iodide. Do I know the moles of sodium iodide? Yeah, that was given to me. 0.405 moles of sodium iodide. What do I do? Units cancel. Do I have the answer I want? Yeah, which means punched into the calculator, we're done. 0.405 divided by 0.724. Mostly happy. Make sense? That was a little short, so should we try another one? Yeah? Molar phosphoric acid solution. Okay. We've got a bunch of stuff in the English language. Get out of the English language kind of as fast as possible. What are we being asked to solve for? Molarity. What is molarity? Cool. Moles over liters. Moles of what? Calcium hydroxide over liters of that solution. What information am I given? I'm given 13 milliliters of calcium hydroxide. Technically, there's a solution on that. SOLN stands for solution. What other information is given? $25 milliliters of our H3PO4, again, technically solution. And what else is given? Molarity. And what does molarity mean? Moles of our H3PO4 over 1 liter of our H3PO4 solution. Okay. Got a bunch of given information. We've got our equation started for us. Start putting it together. Write down what you see and see what you can navigate through. If you got questions, raise your hand. I'll come to you. Like, oh, I learned this fancy equation that works. No? No is the proper answer because it doesn't. It doesn't work. It's flawed massively, and if you have to take more chemistry, it'll be exploited against you and you will fail miserably. Okay? So much so that I'm not going to mention it. So if you haven't heard about it, good. That's the way it should be. Okay? Tutors will try and push it, and it's the wrong approach. Okay? So where should we start? Start with 13 milliliters. Okay. So when you start with 13 milliliters, we're doing this?
No, I put it in his denominator.
Okay. So when we go through and pick something to start with, it's not just I'm placing it in the numerator. There's a logic that has to run with why you're picking it and where you're placing it. So you want to place it in the denominator. Why?
Because then I'm going to cancel it out and do a conversion to liters. So liters probably on the bottom.
You're not wrong, but you're now propagating a calculation a couple steps ahead. Can we slow that down a little bit? Liters of solution is what we want in our denominator for our answer. And we want that for our calcium hydroxide. If we take a look at our blue, milliliters of calcium hydroxide, that's calcium hydroxide solution, and it's a volume. Liters is a volume also. Since I have liters of volume in my answer in the denominator, when I bring in the liters of the calcium hydroxide, it also needs to appear in the denominator. So I'll put 13 milliliters of my calcium hydroxide solution. That sets me up so that I can get my volume in the denominator for the answer. What appears in the numerator? 1, because that's the given piece of information. Okay? What I'm using is the numerator, denominator, the fraction to tell me what I want to do with that given piece of information. Okay? And then you're right, milliliters is not what I wanted. So what has to happen to the milliliters? They have to cancel, and I would need the liters for my calcium hydroxide solution to appear. Do I know that conversion factor? Yeah, this is supposed to be memorized. Okay. What did you memorize?
1 goes with the milliliters and then 10 to the -3.
Okay. Thank you. Okay. So now we have that conversion set up. Now what? Could make the argument the milliliters of solution cancel. We've got liters of solution where I want it in the denominator. Still missing a lot. I'd also argue we've used that, so we don't want to use it again. So now what? We got to use the other parts. The question becomes, how do we use the other parts? So I'm looking for the thing that looks like moles of calcium hydroxide. Do I have calcium hydroxide in those other parts? That's problematic. Do I have moles in those other parts? Yeah? Okay, that's the same measurement. Let's give it a shot. Let's see what happens. Moles of our phosphoric acid per liters of the phosphoric acid solution. 0.01 moles, yeah? Okay, so I've used that. Now what?
Get rid of liters of solution.
Okay, so you decided you don't like the liters of solution. That's fair. Okay.
The liters of H or phosphoric acid solution, not the other one.
Okay, so we want to get rid of our liters of our phosphoric acid solution. Do I know the liters of the phosphoric acid solution?
You don't know liters.
I know milliliters, so what should I do? Okay, so we can write milliliters. I know that. If we're going to write milliliters, I guess I should change that color around. Did that clean anything up?
Not yet.
No, not yet. What do I need to do? I need to convert my milliliters into liters so that those units would cancel, right? Do I know that liter to milliliter conversion? Yeah, 10 to the negative 3 liters is 1 milliliter. Cool. If we process through this information, this was given. This was given,
Wouldn't you need to do the balancing equation?
and this was memorized. That says memorized. Where's the silence? Everybody's like, we can't do anything. What's wrong? Maybe. What's wrong?
You gotta swap the black numbers.
What's that?
You gotta swap the black numbers. You put 1,000 liters for a single milliliter.
No, I didn't. Check the math.
You have moles of phosphoric acid.
Do I want moles of phosphoric acid? No, so what has to happen? What has to happen to the moles of phosphoric acid? It must cancel. I don't have a choice. I got to get rid of it. So moles of our phosphoric acid. Is that the only thing I want to have happen? No, what else do I want to have happen? I want the moles of calcium hydroxide. Does that conversion factor exist? Yes. Where does that conversion factor exist? That's in the balanced chemical equation. Did you write out a balanced chemical equation? No. Can you? Yes. You're responsible for that. So within this question, what are you expected to be able to go through and do? That I take calcium hydroxide, I react that with phosphoric acid. What kind of chemical reaction is that? I'll accept a double replacement. We'd get the calcium with the phosphate. We'd get the hydrogen with the hydroxide. Is the calcium phosphate correct? No, why not?
Because calcium is just
Calcium is a +2. Phosphate,
has a -3.
-3. Is that balanced? No, how do we fix it? 3 calciums and 2 phosphates. Is the hydrogen balanced with the OH? Yes, that's a +1, -1. Now that we've properly predicted our products, what do we now have to go through and do? Balance the chemical equation. And since balancing the chemical equation was something you've already been tested on, we already know you're experts at it, and you should now be able to go through and fairly quickly, hopefully, be able to balance the chemical equation where we need 3 calciums, calcium hydroxides. We're going to need 2 phosphoric acids. That's going to produce 1 calcium phosphate, and that's going to produce 6 waters. With that balanced chemical equation, I know that I have a 3 in front of the calcium hydroxide and a 2 in front of the phosphoric acid. What happens with my units? The moles of phosphoric acid cancel. What units would I now have? Calcium hydroxide per liters of the calcium hydroxide solution, also known as the answer. Now it's just a question of punching things into the calculator. There are some things that I could cut out of this if I felt like. Okay, for instance, I have 10 to the minus 3 in the numerator and 10 to the minus 3 in the denominator, which means I could effectively ignore those calculations, so I don't have to worry about dealing with powers of 10 with my calculator. Make sense? Okay, questions? Kapila? I did see you. Did you guys get it resolved? Okay. So here, we're dealing with that molarity conversion. Okay, but now we expand that to bring in stoichiometry. Stoichiometry is this fancy word that people apply to everything. Stoichiometry applies to one thing, the balanced chemical equation. That's all stoichiometry is. Okay, everything else is just a unit conversion. And even then, what is the balanced chemical equation? Just another unit conversion. Right, that's all it is. How do you convert those units? If you've got a process that sets you up and you ask the questions to navigate, everything goes through and solves for you. But you have to be used to that mindset to navigate it. Much easier said than done. Different question. Where would you expect a question of this difficulty to show up? What's that? Start of the exam? I would change that a little bit, because where should you start the exam? Ooh, this is test-taking strategy 101, one thing that we've talked about again and again and again, particularly when under a time crunch. What question do you start the exam with? The one you know how to answer, that's where you start, which means you have to scan through the entire exam. Is this the one that you know how to answer? No? Okay, this is not the start of the exam. Where would you expect to find this question? It could be the last question you attempt. Logistically, within our exam, based off of how our exam is structured, this kind of a question would show up in a show your work. Okay, why? There's so many intricate steps behind this. I want to provide plenty of opportunity to give you partial credit. So I'm going to place that in a system that would allow you to assign, or allow me to assign that partial credit. Make sense? Do we have another question? What's up? It's okay.
For the chemical equation, I'm not just powder, because you said
That is a different question. In the Chem 130 class, it gets a little bit gray on deciding whether you should know how to do that. You're taking those two substances and you're definitely starting with them as reactants. Are you then, once I write down those reactants, can you look at those reactants and say how they should react?
we should know like double replacements, sure.
And that's where it comes into play. So how should you know that that's your chemical equation? Well, by writing the reactants down, can you predict that it's a double replacement? Or better, a neutralization, though double replacement is easier to work with. Okay, yeah, that's where we'd get you. Okay. If this was a reaction that was a combination, I don't expect you to predict combinations, so you'd be given more context to know that it was a combination or a decomposition. Other questions? So there's nothing you're worried about for the exam? So a sample containing carbon, hydrogen, all that fun stuff is found to have a molar mass of 150 grams per mole and an empirical formula of CH2O. What is the molecular formula? Okay. What is the empirical formula in reference to? Simplified. I don't like simplified because it's a vague term in my mind. If you understand it, it's perfectly fine. I would call it the reduced. Okay, so it's going to come down to different languages. So if we're seeing the formula CH2O, okay, this is our reduced ratio. So our actual compound could be CH2O. It could also be C2H4O2, C3H6O3. Does that make sense? So et cetera, et cetera. And it could go on an infinite amount of time. Okay, so one approach is to just write out all your possible empirical formulas, add them up to figure out what your molar mass is. Because we know the actual molar mass for our compound is 150 grams per mole. Okay, so you can just find whichever one matched is going to be your answer. Right? The other thing that you can do, test-taking strategy, is kind of cheat. Do each of these formulas match the system for CH2O? So is C4H6O6 matching the empirical formula? No, which means that's wrong. C2H4O2, that's actually one of the ones we wrote down. C6H6O6, C6H12O6, thank you. Yeah, that matches C5H10O5, yeah. Okay. Missing information is a little bit of a weird one. Most people don't answer that, so it should actually be deleted from the exam. It shouldn't actually be one of our questions or distractors. Okay. I haven't fixed that for the record, but it's not a useful distractor. So we could go through now and just say, well, what's the mass of carbon? Well, carbon weighs 12, right? 12 times 6 plus hydrogen. Well, there's 12 hydrogens times 1 times 6 oxygens, which is 16, and I could go through and add it all up and just kind of brute force this. Or the slightly more elegant form is that there are ratios. To scale up here, what did I do? I multiplied everything by 2. To get to this one, I multiplied everything by 3, right? What was the mass of CH2O? Well, carbon weighs 12. Hydrogen weighs 1. There's 2 of them, plus the oxygen, 16. Trust you, is it 30?
Yeah.
Is 30. My actual mass is 150. So I can take my molecular mass, 150, divide it by my empirical mass. What does that get me? 5. That's how much it was scaled up by. Right? So how do I scale up CH2O by 5? C5H10O5. There's my answer. Okay. So this is really just getting at, do we recognize what the formula means, and how can we manipulate that to get that information? Does that make sense? Questions about what's up there? I hate this question because you can just brute force this. I think it's dumb. It'd be a good question for show your work, but even then, show your work. You could show your work brute force, and that's still work. It's not very elegant work, but it works. '11 brings in weird units that I'm not a particular fan of, though again, I understand why they want to use them. Formula units is just a fancy way of saying molecules. Which one are you more comfortable with? Then make it molecules. Okay, and I'm going to make it molecules by writing MLCS. Okay, so what am I being asked to solve for? Moles of my potassium nitrate. What am I given to start with? Molecules of potassium nitrate. Okay, it's the same substance as what we want in our answer, so I would place that in the same location. I want to place that in the numerator. Over 1, 8.68 times 10 to the 20th. We got a Google conversion, Word to Google Docs conversion issue, that's a power of 10. Okay, not telling you to multiply by 1,020. Okay, are those two units the same? No, so what has to happen? I need the molecules of potassium nitrate to disappear, and I need moles of my potassium nitrate to appear. I want it to appear in the numerator because that's where it's at in my answers. So now the question becomes, does this exist? And if it exists, what is it? That's Avogadro's number. And what is Avogadro's number? 6.022 times 10 to the 23rd molecules is equal to 1 mole. What can I now go through and do? I can drop the 1 there, 6.022 times 10 to the 23rd. Did I say negative? No, good. What happens? Molecules cancel and I get moles. Now it's a question of punching it into the calculator. This is one that causes problems, punching it into the calculator very commonly. Students will encounter the answer of 10 to the 43rd power, 10 to the 43rd moles, and what's happening is you just don't know how to use your calculator. Thankfully, in this case, you're not being tested on that part, and so if you got that weird power of 10 answer, hopefully you would recognize you just did a math mistake. When you go through and solve this, as in you should solve this and prove you know how to get the answer, okay? If you enter it into the calculator and are getting a power of 10, 10 to the 24th power, okay, you should come talk to me to make sure that you know how to enter it in the calculator and ensure that you don't make a simple calculator mistake. Okay. Questions about that? Okay. Next question. What are you being asked to solve for? We want molecules of bromine. What's our given information? 31.8 grams. Grams of what? Okay. Arguably the question was written poorly and it should actually say of bromine. Okay, on the end of that. Okay. That's really our only given thing to start with, so we could immediately drop that into our expression. The question is going to become, where do we drop it? Should I place that grams of bromine in the denominator or the numerator? Why the numerator? Look for your units. Okay, mass isn't what we want, but the substance of bromine shows up in the numerator in our answer, so it makes sense to keep it in the numerator. 31.8 grams of bromine, what goes in the denominator? 1. Is grams of bromine the same thing as molecules of bromine? Nope, which means I need to run a conversion. I need to get rid of grams of bromine and I need to bring in molecules of bromine. This is something I want to point out because does that conversion factor exist? If you Google it, guess what? It exists. There it goes, oh, it exists. Okay, find it. Where's that conversion factor? Periodic table. Okay. Does the periodic table tell you the number of molecules to grams? Nope. If you're going to look at molecule units, it'll tell you AMUs. If you want to look at gram units, it tells you moles, which means the periodic table does not give you this conversion factor. So Google will spit out a random conversion factor for you, but if that's how you're solving these kind of expressions, you've shot yourself in the foot when it comes to an exam. You need to know where to find it. There is no conversion factor between grams and molecules, or rather standard conversion factor. Just like there isn't a standard conversion factor between centimeters and football fields. Okay? But you can punch that into Google, and Google will come up with a conversion factor to allow you to do that. What it's doing is taking a whole bunch of stacked conversions and putting it together. So what you have to be responsible for, what are each of those stacked conversions? Yeah,
Oh, can I
sure.
so you'd have to go from grams to moles and
Cool.
moles to moles?
So if we want to go grams to moles, so now all that's happening is we're saying that conversion factor didn't exist. I have to come up with a different conversion factor. In this case, we decided I still don't want grams, so I'm going to change the molecule conversion into something else. I'm going to change it into moles. Does that conversion factor exist? Yeah, that's found on the periodic table. Okay? Where we have to be careful is bromine on the periodic table is 79.9. Is that what I should be writing in here? No, because there's two of them. So 79.9 times 2. 159.8, is that what you said? Okay, what happens? The grams of bromine cancel. Is moles of bromine the same thing as molecules of bromine? No. So again, I need to cancel the moles of bromine, and I want molecules of bromine. Is this a conversion that exists? Yeah. Where does that exist? That's Avogadro. Had to slow down a little bit there. Too many C's. Okay, Avogadro's number, we have 6.022 times 10 to the 23rd molecules was 1 mole. What happens? Moles of bromine cancel. We now have molecules of bromine punched into the calculator, and we're done. Okay. We again have an issue with the powers of 10. All of those should be exponents. Make sense? Okay. Hopefully, what's starting to happen is that each of these conversions should be something that you're like, this is boring. We're doing the exact same thing again and again and again. And that is because we are. That's the point, right? Is trying to reinforce the fact that all you're doing is following the exact same process. The only piece of content you need to know is where those conversion factors exist. That's it. Make sense? Questions? It's kind of like pulling teeth to get new questions. Your exam should show those correctly as exponents. That is something I'll scan, and if I see it, I'll have to write it up on the board because everything's already printed. But yeah, generally speaking, that doesn't happen unless it's a copy-paste. And even then, it's only between platforms. Okay, then we're done for today.